So the next question is really interesting, and the topic is bees can sense the electrical field of flowers. So you can think about it that you see a flower, the flower has some color and the flower has some smell, but also apparently there is some electricity in the air that bees can sense and can understand how to land on flowers due to the electric field. So this is gonna be our question. So let's draw a flower, first of all. So a flower is looking like this. Let's put here, this is a flower, it's some kind of a disc, right? Let's do it a simple flower. And here you have it, and some leaves, right? This is wonderful flower. And above the center of the flower, let's put a bee, okay? Here, a bee, hop, 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 hop. This is the head, wings, right? Perfect. Let's call this point B, which is the location where the bee observed the flower. And this flower has some charge density inside. Let's write the charge density. The charge density is sigma P0 R squared. And what I want you to notice about it, P is from the word positive. Okay, so it's a positive value, and R squared is always a positive number. So this is always bigger than 0, which means the flower is charged positively. And you can see that the charge is going up, up, up as you go far away from the middle. You see it? Here is the maximum, and here is the minimum. And the radius of the flower is capital R. Perfect. And the first question gonna be, what is the contribution of contribution to the electric field which the bee sense only from dq. Let's write the dq. Here it is, dq. So here I have some small charge. So the question is, what is the contribution to the electric field which the bee sense in location B? So let's write dE, right? It's a small contribution. That's the reason I put this small e, and I put the letter B, which means the location here. We know that this is equal to what? It's equal to K Q divided by R squared. This is not this. It's not the same R. It's, let's put here D, which means the distance. Okay, so you're not gonna get confused by the radius. So what is this value? So I know what is the Q we are talking about. We're talking about only this contribution. So it's K dQ. And what is this D? I can actually calculate that. You can see that here I have some nice triangle. I can say that the height of the B is H. And here, okay, sorry, this is my triangle, not this one. This is, I want more general form. And this is the location where, here it is, where is my dq is located. If I use polar coordinates, I see here that I have radius, so it makes, and this is a disc, the flower, right? It's similar to a disc. So I can already sense that I need some polar coordinates. D is actually the Pythagoras, right? This is D, the distance between Q and the location. This is D. So I know that D in general is R squared plus H squared, right? This is it. I can also go farther and find dq. What is dq equal to? We know that dq is equal to ds, right? Let's do only this. It's ds is the area, this small area, this surface, multiplied by the charge density. So ds is equal to dr, right? I have some movement at the radius direction, and also I have here r d theta, right? So this is the area that I have, and what is This one is P0 R square. So in general, what I'm gonna have this value, let's write it here. DEB is actually equal to K. I have here R to the third, P0, right? And here I'm gonna leave that as D square. I know what is D is this. And I also have dr, d theta. Perfect. So we found what is the contribution for each small dq, right, on this disc, on this flower. Each this have the same contribution. This one, it's only depend on the radius, right? Because the charge change in the radius. If you're gonna choose this one, it's gonna have a minor effect, but this one will have a bigger effect. But also need to take into account that the distance play here. So this one are far away and this one are more close. So there's give and take, some trade-off. So this was first section. Let's go to the next one.